recompute. And while you're recomputing, you're in this state where you haven't converged. So until you come back and you converge to your least cost paths, we call that period of time convergence. Okay. So you should understand all the things that can happen when things go wrong. When routers fail, links fail, advertisements are dropped, how this can lead to the counting to infinity problem, right? And why we have this max on how far up you can count. But also understand what determines that convergence time, how we have TTL values and how we have these advertisement rules that can affect your convergence time, either make it long or make it short. So if we had nothing but this simple baseline distance vector, then the time it takes you to converge is largely dictated by how frequently you send out updates, that periodic advertisement interval, and your TTL, which is how long you hold on to a route when you've stopped hearing advertisements. Okay? And so we talked about these 3 different rules or ways by which you can reduce your convergence time and avoid loops that happen when things change. Split horizon was this notion of, if you are my next hop, I'm not going to tell you about my path to the destinations for which you are my next hop. This makes sense, right? Intuitively, if I'm going through you, why would I try and advertise that route back to you? It's like asking for a loop. Poisson reverse takes that further and says, instead of not telling your neighbor, just tell your neighbor you have a cost of infinity. And there's a very particular scenario in which Poisson reverse helps actually reduce that convergence time. And Murphy walked through it, Alex repeated it again. Walk through that again, make sure you're understanding it. And then poisoning a route is this other way of actually reducing convergence time, where when your route goes away, you immediately tell your neighbors, I have a cost of infinity. And Murphy had this very nice example where you can see how that very quickly reduces your convergence time. So to make sure you're following all of those, I think what's a very helpful way, pick a few topologies. I tend to like these 2, but pick something more complicated. Walk through scenarios where if you fail this link, what would happen? If you had split horizon, Poisson reverse, or poisoning. If you change the link cost, what would happen? If the destination went away, what would happen? And again, I'd highly encourage you to go back through Alex's notes and presentations on how these different optimizations combine. Any questions on distance vector? Okay. So link state, very different approach. Again, a seemingly simple approach. The idea here, kind of the inverse of distance vector. The idea is every router is going to get the state of all links and all destinations in the entire network. And then it's going to use that global information or that map to build this full graph of the network and compute least cost paths over that graph. And then every router is going to just store the next hop for every destination in its forwarding table. Okay, so I have the full topology, I compute the entire path, and then I just store my next hop. Again, it's simple conceptually, but things you should be aware of here is how does flooding work in link state. Right, so remember, if you go back to Murphy's lectures, if you just flood it naively, where you say, when I get a packet, I'm going to send it to all my neighbors other than the one I received it on, you can have this exponential growth in the number of messages that are going around. And so link state was doing this thing where it's remembering the highest sequence number. So it says, have I seen this message before? And if not, then I flood it, otherwise I suppress it. And that's how flooding is reasonable for link state. Also, problems you can have during convergence. It's easy to underestimate them with link state, but you still do have problems during convergence. And then in addition to knowing exactly how distance vector or exactly how link state works, be comfortable with how they differ at a high level as an approach. Right? So distance vector is this global computation where everyone's computing paths in a distributed fashion across the entire network, but you're doing it using local data based on what your neighbors told you. Link state is almost the inverse, where every router is locally computing the paths, but it's doing that using global information about the entire network that it's collected. Okay. And finally, the last approach was learning switches and STP. Why did we want this? Remember, in all the IP routing distance vector link state, we said your host, the location of your destinations was kind of statically put in at routers, so routers knew where destinations were. But what if you had this kind of plug-and-play network where you can take a host and move it from one place to another, or if you didn't have those statically entered routes? So then learning switches and STP is a very elegant way of doing this. The basic idea is that you're going to learn routes from watching where data packets come from. So when host A tries to send a packet to B, the router that receives it says, aha, I now know where A is. And you can learn accordingly from where data packets come from. If you don't have a route, you're going to flood. And the way STP does flooding is different from link state. Right? Instead of doing what link state did, in STP, flooding works by first building this loop-free topology. Okay? And so we do that using the STP protocol. You should understand why, with learning switches, we have a different approach to flooding. Okay. Anyone remember? How is link state making flooding scalable? Yep. Yeah, so link state had sequence numbers, and it said, have I received this link state update before? It could do that because it was actually storing that link state update. Right? So it had some local state to compare to and say, yes, I have it, or no, I don't. And it could store those link state updates because it's controlled state, and there's not that much of it, so it's fine. And it was going to store that state in any case. With learning switches and STP, we're talking about flooding data packets. So there's no way a switch or a router can store all the data packets it's seen and say, aha, I've seen this data packet before. So we need a different approach, and that approach is to build this spanning tree. Okay? So be comfortable with why you need a spanning tree, how it's used in learning switches. It's used for how we flood data packets, and then also know how we actually build STP, which is building the spanning tree is very similar to how we did distance vector, with one major change, which is that we're simultaneously learning what the root of your spanning tree is, as well as your path to that root. So remember, STP was, we have one spanning tree that's rooted at a particular root that gets picked based on the ID. And so when we flood packets, we only flood it over this loop-free spanning tree. Know the pros and cons of STP versus something like distance vector and link state. STP and learning switches have this nice plug-and-play property for destinations. On the other hand, this entire idea of just disabling a certain number of links is not the most efficient way to be using your links and your bandwidth in the network, which is why learning switches and STP are typically used in fairly small networks. Any questions on intra-domain routing, or those three routing? Okay. So where are we? We went from links to routers to topologies to how we actually route over those topologies. At this point, we have all the components we need to start thinking about domains and inter-domain routing. This is a picture from one of Murphy's lectures where we said that routing within a domain, by which I mean the routing used to reach a destination within a domain, is what we call an IGP routing protocol, or interior gateway protocol. And distance vector and link state are examples of IGP protocols. But we also need some solution by which we learn about routes to destinations not in my domain, right? Destinations somewhere else. And that was the inter-domain routing problem, and our canonical protocol there is BGP, or the Border Gateway Protocol. And the inter-domain routing problem, this is referred to as EGP, or Exterior Gateway Protocol. Okay, so BGP is an example of an Exterior Gateway Protocol, or an EGP. Link state and distance vector are examples of your interior gateway protocols, or IGP. Okay. So again, intra-domain is to reach destinations within your domain. Inter-domain is so that a router within one domain knows how to reach destinations that are in a different domain. And so what was a domain? We said it was a network under administrative control. You should be very comfortable with what ASs are, this notion that you have an AS number, understand the types of ASs. So we said you can have transit versus stub ASs, depending on whether you're carrying traffic across your AS on behalf of a source and destination not in your AS, versus all you just have destinations that are within your AS. That was a stub. Tier 1 transit providers, these were the top, typically the back global ASs. They're all connected with each other. They all peer with each other. They have no provider. You have to be really, really deeply understand the business relationships between ASs and their implications. This notion of customer-provider relationships or peer-to-peer relationships, the fact that customers pay providers and peers do not pay each other. When we talked about inter-domain routing, we said our challenges there are very different from what we discussed in intra-domain routing. It was scalability and policy. Okay. And scalability, we said that we achieve scalability largely through hierarchical addressing. And we had this example, I'll come back to it, but hierarchical addressing was, just internalize that IP addresses are hierarchical. They're hierarchical at multiple levels. In the structure, the fact that you have a network prefix with a host suffix, they're hierarchical in how they're allocated. So we have this organization ICANN that will give a large prefix to regional registries that will hand out smaller prefixes to someone like AT&T that will hand out even smaller prefixes to a customer AS like Berkeley. And then those prefixes are assigned to different domains, and inter-domain routing works on prefixes. So an entry in your forwarding table that you compute from your inter-domain routing, that's a prefix. And then finally, we said that those prefixes can be aggregated. So this further helps scalability, but within limit, that if we have things like multi-homing in this example, here you can see where you had multi-homing required Verizon to have 2 entries rather than just 1 going to AT&T. Okay, any questions on IP addressing, autonomous systems, how they're set up? Okay. So moving on with IP addresses, we said because we have this CIDR and we have this IP address aggregation, this gives us scalability, but it complicates the IP lookup process. The IP lookup process is now not an exact match on your destination address. Instead, it's a longest prefix match. Okay, so understand longest prefix match and why this destination address matched the 4th and not the 3rd. It's because we're doing longest prefix, not maximizing the number of bits that match. We also talked about how you implement longest prefix match, so you should be comfortable with how this is actually done. We're not, we could have taken an IP address and matched it against all the prefixes in our tables. That would have been slow. So instead, we build this kind of prefix tree, and we have this algorithm where you walk down the prefix tree to find the longest prefix match. And when you find the longest prefix match, then you find the next hop port that you're going to send the packet out on. Okay. So again, taking stock, what we now know, if you wanted to have an AS, you would go, what is an AS? A network that's under a single administrative control. To be an AS, you go out and get an AS number from ICANN. You then set up your AS level topology by either being a customer, provider, or peer to other ASs. You obtain a prefix, which represents all the hosts within that AS. And now the last part in the inter-domain picture that we have to think about is how do we actually establish routes between those prefixes. The big challenge here was policy. Right? We talked at length about what we mean by policy and what are typical policies. The challenge with policies is that an AS is going to want to pick paths based on policy. It has its preferences for how it wants to get to a destination prefix. But we have to allow an AS to implement those policies while preserving autonomy and privacy. Okay? An AS should be able to implement whatever policy it wants and should not have to reveal its topology or its policies, at least not explicitly, to other ASs. We said in principle you could do whatever crazy policy you want, but in practice the typical policies have to do with these business relationships and how money is exchanged. And so we had this intuitive notion of routing follows the money. Okay. We then talked at length about how you would actually implement this policy routing. And we said that in inter-domain routing or BGP, the way policy is implemented lies in how these rules around how you export routes and how you select routes or import routes to a prefix. So the setup was very much like distance vector, but now it's AS is exchanging prefixes and their path to different prefixes. Okay, but we said there are 4 big differences relative to distance vector. I'm going to see if I can actually remember them. One is that you actually advertise the entire path vector, not just the least cost. The other was that you can aggregate prefixes as you go. The third is that you don't have to export or you don't have to advertise a route to every possible prefix. And the last one was, I forget, I believe, okay, it's in the lecture notes, I believe it's not necessarily the highest performance path, right? That which routes you pick are not just a least cost decision, it's actually based on policy. Okay, so where does policy get implemented? It gets implemented in your choice of which routes you're importing and which ones you're exporting. Okay? And this is where GAU Rexford is actually implemented, is in this import and export policy. And so again, what was import and export? So import is when somebody advertises a route to me, which one do I actually select? And in selecting a route determines how I'm going to send traffic to that destination. Okay, and we said